All right, this is journal page 390 for lesson 16.6, and it starts off, write the number in scientific notation. So for number one, when it starts off as 4,200,000, we are going to move the decimal right behind the first meaningful digit there, so 4.2. And then where you have to move that decimal 1, 2, 3, 4, 5, 6 places. So times 10 to the 6th. And we were making the factor smaller, so this will be a positive exponent. Number two, it started off as 0.038. So we move that decimal right behind this 3, making it 3.8 times 10 to the something. And we move the decimal 1, 2 places, but we made our factor bigger, so this will compensate, and it'll be a -2. So we make it smaller to go back into standard notation. Number three, 600,000. Moving that decimal right here would make that just a 6 times 10 to the 3, 4, 5 to the 5th power. Number four. For number four, it started off with a whole bunch of zeros there. So now you got to make sure that you're counting those correctly. And it is 4 zeros. 1, 2, 3, 4, then an 8, then a 0, then an 8. And when we do this, it'll be 8.08. That's a needed 0 there to keep that 8 out there. Times 10 to the 1, 2, 3, 4, 5, -5th power. Number 5 started off as 0.0007, which will be 7 times 10 to the -4th power. And then number 6 started off as 29 billion, 10 million, 29 billion, 10 million. And that'll be 2.9, and we have to keep that 1 there. That 0 and the rest of these zeros we do not need. Times 10 to the 3, 6, 9, 10. 10 to the 10th power. So that's the first 6. The next 4 is us putting them in order from least to greatest. And remember, the first thing we look at is the power of 10 that they go to. So when we look at number 7, there is one of them that goes to the 10 to the 9th power. We know that's going to be the largest, so we just have to look at the first two. 2.3 times 10 to the 8th, 6.4 times 10 to the 8th. 2.3 times 10 to the 8th will be the smallest, followed then by 6.4 times 10 to the 8th, and then the one that we knew was going to be the largest, 5.3 times 10 to the 9th. For number 8, similar problem, except for number 8, they all go times 10 to the -3. So we just look at the factor. 9.02 times 10 to the -3, followed by 9.1 times 10 to the -3, and finally 9.6 times 10 to the -3. Just going by their factors there, that number out front, because the power of 10s were all the same. For number 9, we have different powers of 10, so we're just going solely based on those. And it'll start with 7.3 times 10 to the 7th. Then we'll go to 3.7 times 10 to the 9th. And finally, 5.6 times 10 to the 10th power. And then on the last one that goes like these, number 10, much different powers of 10. So the smallest one here is 2.01 times 10 to the -15th. That's a really small number. Then 1.4 times 10 to the -5th, also small, but not nearly as small. And then finally, 6.3 times 10 to the -2nd power. Again, a small number, but it's the largest out of those three. The last problem, number 11. On number 11, it says, a patient has 0.00, hold on, my eyes are going all googly. A patient has 0.0000075 grams of iron in 1 liter of blood. The normal level is between 6 times 10 to the negative 7th gram and 1.6 times 10 to the negative 5 gram. Is the patient's iron level normal? Write the patient's amount of iron in scientific notation. So let's do that first. So for number 11, that number would be moving it, so it would be 7.5 times 10 to the negative 6th. And does that come between 6.0, but times 10 to the negative 7th and 1.6 times 10 to the negative 5th? Well, they made that pretty obvious for us. Yes, this does go between those two. You can just look at the power of 10 and tell that. And so this would be yes, the patient's blood level of iron does fall between the two norms. This one here and this one here. This is actually the higher norm and this is the low norm. So yes, and here's the scientific notation for it right there. Well, hopefully that helped you out, and have a great day. See ya!